Having examined the structure of a glow discharge, we will now turn our attention to a highly versatile and technologically significant plasma of electrical discharge, the dielectric barrier discharge, or DBD. This is a specific class of non-thermal, non-equilibrium plasma characterized by the presence of at least one dielectric layer in the current path between metal electrodes. This simple addition fundamentally alters the discharge physics, enabling operation at atmospheric pressure and giving rise to a unique transient behavior. The canonical DBD geometry consists of two planar electrodes, where at least one is covered by a dielectric material, such as glass, quartz, or ceramic. The entire system is separated by a discharge gap, typically filled with a working gas at atmospheric pressure. An alternating high voltage, in the range of hundreds of hertz to several kilohertz, is applied to the electrodes. The fundamental physics of a DBD is governed by the interplay between the externally applied electric field and the electric field induced by charge accumulation on the dielectric surface. Let us analyze the sequence of events over one half-cycle of the applied voltage. When the applied voltage exceeds the breakdown voltage of the gas in the gap, a multitude of microdischarges are initiated simultaneously across the dielectric surface. These are not a continuous, diffuse glow, but rather a collection of filamentary, transient conduction channels. Each microdischarge is, in essence, a short-lived, high-current electron avalanche that develops over nanoseconds. Within each filament, the physics is intense. A streamer-like avalanche propagates from one electrode to the dielectric surface. This results in a rapid transfer of charge, primarily electrons, onto the dielectric surface. The accumulation of this charge creates a polarization field which opposes the externally applied electric field. This is the critical self-terminating mechanism. Within tens of nanoseconds, the net voltage across the gas gap, the difference between the applied voltage and the voltage drop from the surface charge, falls below the level required to sustain the discharge. The microdischarge filament thus extinguishes. This self-quenching property is the key innovation of the DBD. It prevents the transition from a non-thermal, filamentary discharge to a thermal, high-current arc, which would occur inevitably at atmospheric pressure in an electrode system of two metal electrodes without a barrier. The dielectric barrier acts as a distributed, current-limiting capacitor. During the subsequent half-cycle of the applied AC voltage, the polarity reverses. The surface charge deposited during the previous microdischarge now adds to the new applied field. This means the breakdown threshold is reached at a lower applied voltage magnitude. A new set of microdischarges is initiated, neutralizing the previous surface charge and depositing charge of the opposite sign. This process repeats every half-cycle, resulting in a temporally stable discharge composed of statistically distributed, short-lived microdischarges. We can distinguish between two primary operational modes. The first is the filamentary mode, which we have just described. It is characterized by numerous, stochastic, and visually discrete current filaments. This is the most common mode, especially in gases like air or nitrogen. The second is the homogeneous mode. This results in a uniform, diffuse glow across the entire electrode area. Achieving this mode requires precise control over parameters such as the dielectric properties, the gas composition, often using noble gases like helium, the voltage frequency, and the power supply characteristics. The non-equilibrium nature of DBDs is their principal advantage. The electrical energy coupled into the discharge preferentially accelerates free electrons to high energies, on the order of 1 to 10 electron volts, while the heavy ions and neutral gas particles remain close to ambient temperature. These energetic electrons are highly effective at driving inelastic collisions, leading to dissociation and excitation of background gas molecules, and generating a high concentration of reactive species, radicals, excited atoms, and ions, without a significant gas heating. It is this combination of atmospheric pressure operation, non-thermal character, and scalability that makes DBD technology so impactful. Its applications are extensive and growing. It is the cornerstone of industrial ozone generation. It is the working principle behind surface treatment systems for modifying the wettability or adhesion properties of polymers and textiles. Furthermore, it is a leading technology in the emerging field of plasma medicine for bacterial inactivation and wound healing, and it serves as an efficient source of ultraviolet eczema radiation.